So I want to talk a little bit about carbon and how it cycles through our biosphere. And we touch on this in other videos, but when we talk about elements like carbon, they don't just appear and disappear all of a sudden in our biosphere. For the most part, they have been here since the beginning, but they just get recycled from one form to another. And that is also true of carbon. And to appreciate carbon's importance in our biosphere and especially to life, I have some important molecules or examples of important molecules that involve carbon. And all of these, the carbons are these dark gray colors. So this right over here, this molecule, this is glucose. Glucose, simple sugar. It's where we can derive a lot of our energy from. This is ATP. You could view it as a more immediate store of energy in biological systems. This right over here is one of many amino acids. The amino acids make up our proteins. This right over here is DNA. And in all of these, you can see the role that carbon's playing. In fact, sometimes the carbon's hard to see because it's closer to the center of these molecules, because the carbon, for the most part, forms a backbone. Because carbon's this really neat element, this really neat atom that can make four bonds. So it can make these really cool structures. But the question is, how does carbon cycle through our biosphere? And we can get as simple or as complex as we want to when we discuss this. But on very simple terms, and this is how my brain tends to think about the carbon cycle, you can imagine the carbon in our atmosphere that's mainly in the form of molecular carbon dioxide. So this right over here, this is CO2. Once again, the carbon is in the middle of there, bonded to the two oxygens. And as much as we talk about CO2, and as important as carbon is to living systems, in fact, our bodies are 18 to 19% carbon by mass. So it's very important for biological systems. As important as carbon is to biological systems and the role carbon dioxide plays in things like global warming, it actually makes up a very small percentage of our atmosphere. It's only about 0.04% of the gas in our atmosphere. Most of our atmosphere is actually nitrogen, 78%. You don't talk a lot about it. And oxygen, 21%. And then a bunch of other elements and molecules. But the very simple version of the carbon cycle is, okay, you have this atmospheric carbon dioxide, molecular carbon dioxide hanging out in the air, and you have autotrophs like plants. And so let's say that this is the ground, and I have a growing plant. So that's a plant right over there. That's its leaf. That's another leaf. And the way that plants grow is they're able to take light energy, so that's energy coming in from the sun, and use that energy to fix carbon. Now, fixing carbon sounds like a very fancy thing, but it's literally taking that molecular carbon dioxide out of the air and fixing the carbon from it to form these different molecules in the plant that help the plant, that give the plant structure, that give the plant energy. And so that mass of that plant, I'm actually in this room I'm in, there's a house plant right next to me. It's not just growing out of, I guess you could say it's growing out of thin air, but the mass isn't just magically appearing. It's taking that mass out of the air. And so that's what allows this plant to keep growing. And so once again, as I said, some of that will be in the form of proteins, amino acids. It could form structural components. There could be fats. And also some of it is energy. And you could imagine other animals that can't do this, that can't photosynthesize. Well, they might want to eat these plants for that energy. In other videos, we talk about the food cycle. And so, this could be me. This could be me having a salad. And I might want to eat that plant. I might want to eat the plant for the sugar in it. Maybe it's an apple of some kind, and then that gives my body the energy to live and grow. And as I metabolize that glucose, so for example, glucose is one of the molecules that plant can form by taking that carbon out of the air, and then I might metabolize that glucose from that plant I just ate, and as I do that, I will release carbon dioxide. So I will release the CO2 back in the air. And then you can see that you can form a cycle here. The CO2 gets released by things that are metabolizing these organic molecules. And then it can get fixed again by autotrophs, which are able to store the energy from the sun in terms of these bonds by fixing this carbon. But there's other pathways that we can have to have these cycles. For example, some of the CO2, it could be absorbed into the ocean. It could be absorbed into the ocean. And in the ocean, it can form carbonate. And so once again, you still see the carbon right over there, carbon bonded to 3 oxygens. And calcium carbonate is a key constituent in things like seashells. And over time, as the seashells break down and get ground up and they get impacted with pressure, and they can form limestone. So this right over here is limestone. But once again, it was formed from carbon dioxide being absorbed into the ocean, living things using that calcium carbonate, the carbonate in conjunction with calcium, in order to form these shells, which get ground down, and it actually forms these rock structures. You can have situations where living things, whether we're talking about the autotrophs like plants, or we're talking about things like me that are eating the plants, that, well, once they die and there's all this organic matter that hasn't been broken down yet, well, it gets buried in the ground. I'll do the plant because it's less morbid than showing me dead. So let's say this is the plant. Well, with enough pressure and time, sometimes in the decomposing process, some of the carbon might be released, but over time, this might be compressed and be turned into fossil fuels. So when you see oil, or when you are burning gasoline, which is really just a refined part of the oil, it is really this organic matter that storing energy that plants were able to store from light energy, possibly millions or tens of millions of years ago. But then if you were to take that fossil fuel out of the ground, which we now do very actively in order to power all of the things that we need to power, and you were to burn it. So let me see. Let me just draw an example of that. So let's say that if you had a canister of oil. I'm not going to do the oil in black because you'd have trouble seeing it. And if you were to burn it, the process of combustion, and this is in general if you're burning anything, it doesn't just have to be oil, it could be burning a piece of wood. You're taking that organic matter, those carbon bonds, and in some ways you could say you're doing the reverse of the photosynthesis process. You're breaking it down, and in that process you're releasing that carbon, and it's getting released in the form of carbon dioxide, which in theory could then be fixed once again. So the general idea, autotrophs like plants, when they photosynthesize, they can fix that carbon, and then it could either be burnt, and the combustion process can release that carbon back into the atmosphere, or you could have other animals eating that plant, and then as they metabolize, as they break these carbon-carbon bonds to power themselves or to just do whatever they need to do, that also can release carbon dioxide.